All right, we can get started. Welcome everybody to the 10th session of the ML Scalability and Performance Reading Group. Today, uh, Han Chi will be presenting his paper on task-specific quantization. Really cool to have the actual author of a research paper come and present his work to us. So really excited about this. With that, Han Chi, take it away.
Thanks for the introduction. I am going to be introducing the task circuit quantization, and the main idea of this paper is trying to combine some of the interpretability ideas with quantization to see if we can sort of cross-pollinate it a bit, and then try to figure out how to compress models more efficiently with these ideas. Um, the particular regime that we're considering here is like somewhat specific. So I will begin with some of the preliminary background, right? Um, this method is based on the GPTQ kind of compensation based quantization, and I'll introduce that, and I'll also introduce mixed precision, which is essentially another thing that we basically utilize in this paper. So um, broad idea is that GPTQ-based quantization uh, not only directly rounds the floating point numbers into basically integers, right? But that whenever you quantize a particular weight and you sort of round it into like a quantized format, um, you take you consider like what you've actually changed the value to, and you try to compensate for that by changing the value of weights that you have not quantized yet. Uh, the idea of the mixed position is the particular one we're considering is that in a particular 2D weight matrix, there may be weights that are much more important than other weights. And for these weights, you basically do not quantize them and you keep them in 16-bit floating points, and instead of trying to do any rounding. Um, so to go a bit of more detail into the sort of the GPTQ kind of thing, just fun background. Like this is an idea that's been around for a long time. It really started in pruning, like even in like the 90s and stuff like this. And basically, people were trying to like remove connections from neural networks, right? But then they realized, well, um, you can really treat these networks as separate layers, right? In the current GCM, this works out very well for language models because they're all different, like very clear layers appear in these models. And what you basically have is they're formulating the compression problem, so the problem of either pruning the model or quantizing the model as a layer-wise reconstruction. So they're taking a look at if I were to remove a particular weight or quantize a particular weight, I want to minimize the impact of the output. So the x multiplied by the weight, right? That of the original model, so the unquantized weights, versus the x multiplied by the quantized weights. And you want to minimize the difference. So you want to minimize like basically the difference between these two quantities. And then the way they do this is through a series of extremely large like extremely large estimations, right? So a thing that will appear is that like in this paper and a lot of these like compensation based papers, there will be a lot of simplifying assumptions being made. Basically, you're trying to obtain the Hessian of the loss with respect to the weights, except you're making a simplification first by saying that you're not considering the loss as in like the final model's output loss. You're considering the loss as in the reconstruction loss per layer. And then, secondly, you're not considering any of the higher order terms. You're in fact only ignoring all the second order terms as well as as most of the other relevant terms as well. And then you're basically simplifying the calculation of this Hessian down into just xt. So this like estimation of the Hessian does not even consider the magnitude of the weights. It just considers basically like the input to that layer. And then, so what you would need so what you would get out of all of this estimation is something that basically looks like this. It basically is telling you how should you change the weights DW, which is the weights that you have not quantized yet, given the quantization that you have currently have applied to the weights that you have already quantized. Right? And so here's a little graphic for that. So what GPTQ does is that it looks at a particular weight matrix, and it actually looks at one column at a time. So it moves from, I guess, technically from the left side to the right side of a weight matrix. And then for each column, it will quantize the entire column. And then after it has quantized the entire column, it will make adjustments to all of the columns to the right-hand side of that column. And then it will quantize the second column after that, and then it will make adjustments to all the columns on the right side of that until it has quantized the entire block. Um,
Can I ask you a quick question?
or is this making sense? Yeah.
Yeah, so just to back up for a second, I'm just not as familiar with like this compensation based approach, so this is like a very naive question, but just what is like the theoretical justification or motivation to um, basically adjust the non-quantized weights column by column like this as you quantize these certain columns? Like what is the benefit they're trying to achieve to doing that?
Yeah. So whenever you quantize a column, there you're changing basically how the output that your model would produce.
Mm-hmm.
Given a data set X, right, you've changed the output
Mm-hmm.
because of the quantization. But you can basically do a step of training in order so that you try to minimize the change in the output.
I see, I see. Okay. So that's where all the hessian is coming from and everything is we're trying to minimize the change in the output as a result of this quantization essentially. And so we're doing it step by step and adjusting as we go. Is that the idea?
Yeah, yeah, exactly. Yeah. So
Interesting. Okay.
that's where the whole like layer-wise recompensation idea comes from. They're trying to reduce the reconstruction loss of the output,
Mm-hmm.
right? Based on this X, which is a small calibration data set.
Mm-hmm.
So this small calibration data set is usually like 128 examples by of like sequence length 2048. That's what's used a lot of times. So like a fairly small calibration data set, and they try to use that to estimate how to adjust the weights.
Got it. And so for this, it just for like later today, if I wanted to go do additional reading on this, is GPTQ the kind of foundational piece of work that I should start with, or is there something else?
Yeah, you should look at the GPTQ paper. Yeah.
Okay.
Um,
Cool.
but so yeah, this is would be what I say to look at. But technically, GPTQ will describe some of the related works previous to this. Like there's some really old works that cover the same idea,
Mm-hmm.
and uh, like so not don't look at OPTQ. I think that's like too similar. But the optimal brain surgeon thing is another good thing to look at.
Okay. Cool.
So
Thanks.
I would start with GPTQ. Um, so now that we have established GPTQ, there's sort of mixed precision quantization, and this is like much easier to explain. It is actually exactly what I said in the introduction, where um, so this mixed precision idea spawns mostly from this like SPQR paper, is where I'm basing most of this mixed precision off of. And this SPQR paper has essentially identified that there is a pretty power law distribution in the importance of weights in a language model. So empirically, it seems like even just like 1% of the weights is like extremely more important than 99% of the weights. And if you were to basically keep 1% of the weights in a higher precision, yeah, you would like be able to improve the sort of the accuracy. Well, to preserve the accuracy of the model much better. So in fact, the 1% it might not seem like much, but like empirically, I've observed that it's actually more like 0.3%, point even sometimes 0.2%. You can already
Hmm.
see a large effect. And other papers have actually observed that just by like accidentally quantizing a few weights, like a countable number, like maybe 5 weights, you can destroy the entire performance of a language model, right? But
Wow.
if you preserve these 5 weights, your performance would like recover incredibly well. Um, and but if you were to instead select some other random weights to preserve and not these very important weights, then like it would have no impact. In fact, if you were to preserve like a million other weights that are not important, it will not even have like nearly the same effect as if you were to preserve just those 5 weights that are actually extremely important. So does that the idea make sense?
Yeah, that makes sense to me. That's really interesting. I didn't realize it was such a small percentage like that because I've seen in practice people leave certain layers in high precision, like leave
Mhm.
I don't know, like the routing layer and like MOEs in like BF16, but do like just the like the actual FFN computations in like float 8 or something. Just to
Mhm.
certain layers are like more sensitive to low precision. I didn't. That seems like a very coarsely grained way of doing it now that you're sharing this.
Yeah, yeah, it's definitely pretty surprising. So this Super Weights paper might be something good, interesting to look at. I think they had a
Hmm.
very nice analysis on like point zero 0.01% of weights will even do this like very well.
Wow.
Um, let's see. And yeah, and the difference is like 10-20% on like MMLU. So like okay, and so now that I've established these two things, what I'm essentially doing in this paper is I'm taking a look at improving mainly two aspects. The first is that I noticed the way people have been identifying important weights has not really been optimal. So they've really looked only at like super simple ways of identifying these weights. So by just using the raw gradient value to the weight over that data set, or using a very local measure, such as like the magnitude of the weight itself, or in some cases, whatever the GPTQ algorithm tells you. So the GPTQ algorithm will tell you something that's in reference only to the layer-wise reconstruction. So it will be like a very local metric for what weights are important. So I'm basically developing a better way of finding out what weights to preserve. That's the first part of this paper. And then the second part is I noticed people were using a calibration data set in order to quantize these models. And these calibration data sets are almost always just like batches of pre-training data. And it's like oftentimes it's actually like in the official implementations of these papers, it's like somewhat non-trivial uh, to change the code such that you can like have data sets that are not samples from pre-training data because they sort of enforce this like every single data point must have the same sequence length or the Hessian will not be able to be like accumulated properly. Okay, so um, people really haven't really considered conditioning on like task specific downstream data, and then basically being able to show that actually if you condition on task specific data, you get like fairly large and very noticeable gains in these very low precision scenarios. So the focus of this paper is mainly in the very low bit compression, so compression to 3 bits and compression to 2 bits. Um, right now, with compression to 3 bits, I am able to recover like 96, 97% accuracy of the 16-bit model. And then at 2 bits, with significantly less. But uh, that's kind of how like 2-bit compression goes, right? Like 8x compression generally destroys the model, at least at like 7B, 8B kind of small scale language models. Um, yeah. So, like, to give a quick sort of um, summary of the method, um, what I'm basically doing is uh, using sort of a automated circuit discovery kind of angle of looking at this. So in the automatic circuit discovery literature, there's a lot of emphasis on, uh, well, there's been a few recent works on using the gradient uh, difference. So using a Taylor approximation in order to approximate the change to the final loss depending on some change in the input of a model. So what they do is they would have like a corrupt model and a non-corrupt model, where the non-corrupt model is just your standard model with the standard inputs, and then the corrupt model is the standard model but with inputs that are corrupted in some way, such that the model no longer gives you like the correct output anymore. Right? Then what they do is at every intermediate activation, they would take the difference between the activations from the clean model and then the activations from the corrupt model, and then they would multiply that difference, right, with the loss, I mean, with the gradient to that particular activation. And then they would use that to say, okay, this is basically the impact of a particular activation of a particular like sort of area in the model. If you were to corrupt it, like what would be the like so the contribution of that particular part of the model to the corruption of the model's final output. Obviously, because we're dealing with quantization and not like this sort of like trying to find circuits which are based on activations, I basically switched it so that instead of looking at using the activation difference and the gradient to the activation, I'm looking at instead the gradient to the weight as well as the difference between the weights. So I am looking at the clean model as the normal model again with the normal inputs, and I'm looking at the corrupt model as a naively quantized model with the clean inputs.
Hmm.
Um, and basically, I do a little bit of math and I explain that basically this is like pretty much invariant. The math work out to be basically exactly the same thing. And like theoretically, it's also pretty much equivalent because the fundamental principle is basically the same. Um, what this end up giving you is like basically like if you were to, this is a metric that gives you a score for every single weight in your model, and the metric tells you if you were to quantize a particular weight, how would the eventual output of the model be impacted? How will the performance of the model be impacted if you were to quantize a specific weight? Uh, and then like I use some assumptions and like estimations in order to make this sort of like make this metric specifically that whenever I like take the difference between the quantized model and the normal model, I'm doing like sort of a naive quantization where I don't actually hold out any weights in 16 bits and I'm just like naively quantizing it. Um, that's a bit of like an approximation of what's actually going to be happening later on. So it's not like an entirely 100% accurate metric. It's fairly accurate because I'm only like ever going to be holding out like 0.3% of the weights in 16-bit. The second part of this is basically I'm doing it with respect to I'm integrating some ideas from GrabCAM, which I think should be pretty much familiar um, to everyone. So this whole line of work with input attribution has essentially, in my opinion, culminated to a very nice observation that a large section of these input attribution methods have reduced to the gradient to a particular input multiplied by the magnitude of the input itself, which actually happens to be basically the same mathematical logic as we saw in the previous section. And this this kind of metric has also been pretty much used in pruning a lot, where you would take, you do the same thing that we did earlier, where we swap the activations with the weights, and then you do weights multiplied by the gradient to the weights, and that basically estimates um, what would be the impact to the final performance of the model if you were to remove a weight entirely. And that gives you a fairly stable estimation of like basically in the importance of a particular weight in general. Then my final metric for selecting what weights are important is basically just a combination of this like magnitude sharpened gradient thing, which is from input attribution, and this quantization aware localization thing, which is from the sort of automatic circuit discovery literature. Uh, yeah. Any questions so far?
Yeah, I'll let somebody else go because I've been talking. Did you wave function? Did you want to say something?
Yeah, just quickly, I was wondering, is there like a mathematical justification for the TAC-Q equation beyond just that you need to account for the, the size of the weight versus the how close it is to the quantized version?
Mm. Yeah, yeah, I can explain that part. So I kind of skipped over it when I was going over this, but basically, um, this whole thing is dependent on the using looking at the gradient as a first order Taylor approximation of how much the loss
Mhm.
will change, right? So the gradient obviously
Yeah,
gives you
no,
like sort of like a hyperplane, right? Yeah. Okay, I've only
yeah, I
if you
think
already
I understand equation
yeah.
four, and
Mm,
I think I understand the justification, the sort of the practical justification for the
yeah.
TAC Q formula. But is there, and I'm just wondering, is there like a some kind of like optimization formulation or something like that, which the TAC-Q formula falls out of, or is it purely ad hoc that you need to account for the size of the weight in the case where the quantized version is close to the actual weight?
Um,
Because that was my understanding of the justification for equation seven. That like we want the quantization aware localization, but that's going to break when QW is close to W. Um,
mm. Oh, okay, I see. Like whether or not, like why this composition has to happen, where I have to consider both this part as well as the magnitude part.
yes, yeah.
I see.
Yeah, is there another way to justify that apart from the pragmatic aspect that like the final factor there could be small by accident?
Yeah. So there's not like an optimization formula or something nice, unfortunately, to connect these two. It's mostly practical. This particular
Um,
section, I haven't put all the reasons for it. Um, in the appendix, there's some other reasons, but like there's some like other practical reasons other than the fact that it could be very small and that estimation could be very noisy, and therefore you want to like basically stabilize it with the magnitude. There's also a reason that it happens that because linear quantization always places a grid line at zero, um, and the most of the weights are in sort of like a normal distribution around zero. It means that just in general, that the magnitude sharpened gradient is a fairly good estimation of like how much the weight will move as well.
oh,
There's a
interesting.
few other small tidbits like numerical precision and stuff, but yeah, mostly practical.
Thanks.
Thanks. Um, then did you have something, or should I move on to the next section?
Oh no, go ahead.
Okay, great. So let's cover some results, right? Because I mean, obviously it has to practically work, otherwise there's not really a point. Um, so uh, I'll describe a bit of the testing methodology. Basically, I wanted to test on both the like, multiple choice kind of questions, which is like, in my opinion, the more prevalent way that people have been testing things, perplexity and multiple choice questions. But I also wanted to test on questions where the model is asked to generate tokens because the quantization error, in my opinion, like accumulates as you generate more and more tokens. So I have a text to SQL task spider that basically, like natural questions, and then the model is supposed to give you a SQL query, as well as some like GSMAK where they have to give you like a chain of thought. Apart from this, there's also like the NMLU, which basically we divide into four different, well, we divide into the whole NMLU as well as three separate like NMLU tasks based on the original split in the paper. And we actually consider them basically as entirely different data sets. So we would condition on the questions from, let's say, like STEM subjects, quantize the model, and then we would evaluate the accuracy on like a held out, like a validation split uh, on the same sort of STEM type questions. Um, yeah. So the baselines we consider, I'll briefly go over. So SPQR, uh, fairly similar to uh, our method in terms of it's doing like GPTQ based quantization. But it is additionally doing double quantization as well as, which is like a slightly more efficient way where you also like quantize the quantization scales that you use to quantize the model. But that part is not super important. But it selects what weights are important to preserve based on the GPTQ metric, which is a layer-wise metric. SqueezeLM uh, does like sort of like a code base uh, based sort of quantization, which is also not very important to know about right now. But it selects weights based on the magnitude of the weight. Most of the weights that it selects are based on the magnitude of weight, and then a tiny portion of the weights it selects to preserve are based on the squared of the gradient, which they refer to as Fisher information. And then SlimLM has the same metric as SPQR, which is the layer-wise GPTQ metric, but it's like more fine-grained, so it can like select basically blocks of a weight matrix to place into higher or lower positions, like dynamically. So in general, we observe that SlimLM performs like a bit better than SPQR and SqueezeLM, and TAC essentially outperforms most of them, especially at 2 bits, where we see that like basically like sometimes we double the performance of the previous methods. Uh, was pretty much the same like bit width. So we try to make sure that we give all the prior methods like more bit width, because a lot of the prior methods tend to like utilize thresholds, which like means that it's like kind of hard to specify exactly what bit width you're going to get out of the model, especially because we're conditioning on all these like different data sets. Um, yeah, so nice Pareto plot, right? Like you know, Pareto frontier, whatever, where we do like bitness scaling. So one fun thing to note here is, um, in general, like you do not want to try to scale this sort of outlier like percentage. Like if you were to hold out 0.3% of weights as outliers, you get massive improvement. But then if you held out like 2% of the outliers, you incur a very non-trivial cost in terms of average bitness. Um, Specifically, if you wanted to hold out like even just like 1 or 2% um, like of well 2% of weights in 16 bits, your average bitness now balloons to something like plus zero point 0.8. Right? So if you were like doing qubit quantization and you did like 2% like outliers, now you're basically doing 3-bit quantization. Um, because for every like 16-bit weight that you want to hold out, you're incurring something like 32 bits in order to store that weight. Because not only do you have to store the value, you have to store where it is in the actual weight matrix, and that turns out to be a lot. Um, and yeah, generally, if you scale this, like you don't want to scale it too far so that you hit the like basically basic GPTQ will beat you if you were to have too many if you were to use too many outliers and you get to like the three-bit regime. This is generally true for all types of quantization methods where you rely on like outliers and preserving outliers. There's some other interesting little tidbits. So we're the only method that recovers like uh, ability to generate on Spider. So previously I mentioned the Spider data set where you have, yeah, there you go. You ask something like, what are all the distinct countries where singers above age 20 come from? You give the model a like database schema of how the database is laid out, and it's supposed to give you an answer that looks like this. Um, it happens that when you do two-bit quantization, most of these methods like they either lose the sort of instruction following ability and they just start like generating text, or they give you empty results or like sense text or like repetitive text. Um, so that's kind of interesting. And then um, it's almost like in like some quantization, like quantization up to different levels will like induce qualitative changes in model behavior sometimes. Uh, I'm not sure if this is like entirely consistent. I haven't investigated it closely, but it might be the case that at some like threshold, you might lose like entire classes of behaviors, such as being able to follow instructions or something like this.
Mm.
Right. Okay. So other thing is, we test all of our methods in the main tables based on conditioning on the particular downstream task that you're going to use the model for. But we also tested, okay, what if we use the TAC and basically like condition it using a normal pre-training data set batch, which is what most other quantization methods that depend on calibration does, which is they condition on maybe like a few sequences out of the C4 or out of the Wikitext2. In this case, we did based on Wikitext2, and we see that still that we outperform the other methods, 7.7% in terms of like the ability to perform on a downstream task, uh, if we were to condition on on a particular on a pre-training database batch. Um, but also we show that like in general, if you were to just condition on things, like if you were to condition, let's say for like squeeze for SlimLM, condition on Wikitext, like this is like random accuracy. Right? But if you condition on something that's like somewhat similar, so this is we're testing on MLU humanity split. If you conditioned on the STEM split, you already get like a 6-point boost in your performance. If you were to condition on the exact humanities split, you would get like almost like a 10, 12-point boost in your performance at low bits. Like the relationship is less clear in 3 bits, but you're still getting like 3.2-point boosts for 3 bit as well. And this is like very consistent across different methods. Like immediately like 10-point, 20-point boosts. Uh, uh, let's see. Uh, so another kind of fun little thing here is I tested out. I didn't include all the tests that I did in this table, but here some of the interesting ones are like different ways that people have selected weights to preserving 16 bits, and uh, weight magnitude, which is very popular and like a big thing in tuning, does not do very well for quantization because we're not actually like destroying making the weight zero, so it's not like a good estimation of how important a weight is basically at all. And then there's a lot of papers that do this thing called the sample Fisher, which is like an estimation of an estimation of the second order Hessian information of a particular weight for a particular weight. Um, and what I observed is that technically, um, this is basically equivalent to the gradient because what ends up happening is they make so many simplifications that the eventual metric is just the squared of the gradient per sample. Then empirically, it performs also basically the same thing as the gradient. Here it's the sample absolute gradient, and it like the performance is basically the same. Um, and then the reason that this thing, the sample gradient, is not good is because the sample gradient basically doesn't like take the absolute value of square the gradient, which means that if like you get a gradient for each sample in your data set, and sometimes the gradients cancel out, and we don't really want to cancel them out because we're trying to figure out how much the sort of how much we expect a particular output to be affected in either direction. So we don't really care about the direction of the gradient. Um, and here's some ablations on the TAC method. So if you did just the magnitude sharpened gradient or just the quantization aware localization, you get still an increase from whatever the sample gradient is. But if you combine both of them, you get an additional increase. Not directly additive, but it's like pretty consistent and pretty clear that if you have both of these methods, that it's empirically better if you combine them. That pretty much covers it. Uh, yeah, there's some like other kind of results, but is there any questions
Did
or
you open
comments or anything?
Um,
did you open
yeah.
source any implementation?
Yeah, so we have GitHub of like the quantization algorithm. I'm not unfortunately good enough with CUDA to make kernels for it. So
Hmm. Cool. Okay, I'll take a look.
Uh, I'm not sure what you're showing in table two. So the sensitivity measure, what exactly is it sensitive to? The impact of changing the weight
uh,
um,
table two,
on the loss? Yes. Oh, sorry, table five.
table five. Okay. Let me find. Yes, this one.
So why is it important that TAC-Q have a higher value for this sensitivity measure? What
Oh,
exactly?
yes. Yeah, it's a bit hard to see, but this here, the numbers is the eventual downstream accuracy.
Oh, I see. Oh, right. I get it now. Yeah, got it. I'm
Yeah.
sorry, I just didn't read that.
No, yeah, we didn't format it super well. It's like almost run into this. Um, yeah. Let's see. Oh, yeah. There's a little thing here. Oh, not here. I mean, we also evaluate on Quinn and we evaluate on a larger model as well. So the SearchEV instruct. Um, turns out obviously that larger models are easier to quantize, and with 2 bits you can already get something like a 87% react recovery on the performance of the full unquantized 16-bit model. That's kind of fun. Oh, I should probably caveat with saying this is like fairly standard, right? In most of the weight-only quantization, that we consider the baseline to be the 16-bit model and not like a 32-bit model. Uh, the accuracies are basically completely the same between them. Um, oh yeah, another fun thing. It turns out the gradient is very robust to the number of samples we use for calibration. Um, like obviously like the downside of our method is that you have to actually condition on some downstream data points if you wanted to use the conditioning part of our method. But it turns out you can reduce the number of data points you use for this conditioning and basically not impact the end performance, or at least for capturing of the gradients. So you can use 16 examples as opposed to 128 examples, and you get exactly no impact to the accuracy performance. So I was kind of surprised that this is the case. But I read some other papers that had similar results where they use like metrics that are basically just based on the gradient. And it seems like anything beyond 10 examples, it gives you like a fairly good estimation of the gradient. Um, yeah, there's another thing um, like quantization timelines and the quantization resources. I've always been under the assumption that like since quantization you only do it once, like it's fine to use a bit more resources. But I started thinking about this a bit more, like what is the actual difference between using a gradient-based method versus a like layer-wise method in order to quantize your model? Like what is the GPU memory overhead here? Turns out for layer-wise, it's like very small, right? Because you're only considering one layer at a time, whereas gradient I assumed, load the entire model in. And that's the way that I'm basically currently doing it in the implementation. But I realized that um, because the time spent for quantization is like not actually very much, and the amount of data points that you have to use to capture gradients is not very much. Uh, I theorize it's like fairly possible for you to load one chunk of the model at a time and then backpropagate one chunk of the model at a time. So then you reduce your GPU memory overhead. But it seems like a somewhat non-trivial to do engineering wise.
Sorry, I didn't really follow that. What chunks of the model would you be loading at a time? Like, are
Uh,
you talking about layers or?
yeah, I guess in this case it'd be layers. So if after you get the loss from the model after you do the forward pass, uh, and
Mhm.
you now want to compute the gradients with respect to the weights for the backward pass, you could load like one like language model layer at a time. It doesn't have to be one linear layer, right? It could just be one of the layers with the attention and the NLP, right? So one of these layers, and then you
Yeah,
compute the
totally.
gradient, yeah, and then you like unload that in back into the CPU, and then you load the next portion into the GPU. Um,
And that would allow you to quantize larger models, essentially.
yeah, exactly.
I see. Thanks.
Yeah, that seems very doable. Just maybe make an implementation that needs to happen. Uh,
Yeah,
that's cool. Well, this is really interesting. I really like the inspiration from the automated circuit discovery concepts. I learned a lot from this. Yeah, do you have any? Do you? I was wondering, do you have any ideas on like future directions for this work, having done this?
yeah. Um, so I think the next steps are like I mean like you have to make a kernel for this kind of thing in order to have it work efficiently. Um, so it would be nice to like make good kernels for this sort of like mixed precision. Um, the current approach has basically been you do like quantized matrix multiplication for the quantized parts of the model, and then you do a sparse matrix multiplication for the 16-bit values that you preserved, and then you add them together. Like this is not very efficient, and also
Hmm.
it's like kind of limited by the skill of the kernel writer, and also like if your CUDA version updates, like it breaks. Like I've seen it
Hmm.
break already on some of the previous repos.
That's
Um,
interesting. Wait,
that
so
yeah.
I was just gonna ask really quick. So, but wouldn't this is probably a silly question, but since the weights that are quantized versus not quantized is done dynamically based on like the task specific conditioning you're talking about, wouldn't the you can't really like handwrite a kernel ahead of time to do that, could you? I guess I don't know. You have a more concrete understanding of this in your mind. So, is there a way to like generalize a kernel that can like basically know, like I don't know whether it's like via input arguments or in some way it can, dynamically do this rather than like hard coding it ahead of time.
Uh, yeah. So the kernels I'm more talking about is like generalized kernels. So even the generalized kernels for doing multiplication for sparse matrices are not even good. So this is
Hmm,
not even like a optimization for the specific weights
I
selected yet.
see. Huh. Okay.
Um, it's like here, let me give you an example, right? Like the SVQR paper, um, they are able to obtain a 20% sparse 20. Well, okay, I guess it's kind of hard to find where they say this, but they gain a 20 to 30% like performance improvements, like efficient, like speed wise, compared to the 16-bit model. They use a specialized sparse multiplication kind of thing as their kernel.
Mm-hmm.
But if they use like the normal PyTorch implementation of the sparse multiplication, it's actually like basically the same speed as a 16-bit model.
Really? That's interesting.
Yeah,
Mm.
yeah. Uh, yeah. That's that kind of caveat, right? And then the second part is like the capturing. Like I really want to make that thing where you can like have low memory overhead, but still be able to capture gradients, because quite a lot of other things also rely on capturing gradients for a small number of examples, and then be able to use them. Like various like pruning stuff, like model merging can gain some things from that as well. But it
Mm-hmm.
seems like it's like PyTorch has made it non-trivial because apparently it saves the like uh, computations in GPU, and there's like a different class like for the computations depending on whether or not it's in the GPU and CPU, and you have to like swap this, and I have to look into that more to figure out
Hmm.
what how exactly that works.
Torch has some kind of zero uh, uh, training scheme, surely, where each GPU is responsible for uh, a particular layer, for instance, or a particular set of weights.
Hmm.
Um, it should be possible
Yeah,
to do what you want uh, in terms of however they're arranging things there, in my
yeah,
opinion.
yeah. That's my hope as well. Um,
Mhm.
but yeah, right now, like on in terms of like the less engineering side of things, like I've been focusing on a new project, so I haven't looked too much into implementing that GPU thing yet. Um, but in terms of like ideas for like next steps based on like the non-engineering side, I would think this can very easily be expanded to like multimodal models. They have like slightly different dynamics. Um, I think they should pretty much work the same, and but it might be good to test that. And then the other thing is, um, this is like very bare bones in terms of like the methodology that I introduce. It's, in my opinion, super composable. The only thing that you need to make this TAC metric work is that you have a naively quantized model as well as a normal model. And the naively quantized model, like it doesn't actually matter what kind of quantization method you use. Currently, we're basing it off of GPTQ. but GPTQ is not the best kind of method for like this sort of compensation-based quantization anymore. And you can definitely replace this with a much better method, like a code-based method or
Methods.
k-means based.
Okay.
Yeah. And then uh, and then there's like other things like thresholding. So a lot of previous methods used nice thresholding schemes, which are able to basically improve their accuracy. Like for example, um, you can instead of specifying exactly how much weights you want, you can dynamically figure out what would be the best number of weights to preserve per layer based on some metric. Um, and then you can like use a threshold to like adjust that. Um, if you did that sort of thing, I think it would improve accuracy, but like it will have the obviously side effect of now it's harder to specify like what exact bit width you're compressing your model to. You have to do a grid search and stuff like this. Uh,
What was the other method you mentioned apart from k-means?
other, you mean like the baselines or
Oh, you were saying that you're using the GP whatever
Q?
method for
Yeah.
quantization for your Q function, and you mentioned k-means as an alternative. What was the other one you mentioned?
So there's some like uh, such as learned quantization. So like, for example, this paper called OmniQuant. Um,
Cool.
instead of using like a nice like so GPTQ is one step. It uses like a Cholesky decomposition to figure out like how to adjust the weights, and then k-means obviously just uses k-means, right? But these guys
Mhm.
actually learn the values that like learn how to quantize a particular weight uh, using like gradient descent essentially. You could do it. It's this.
Have you experimented with other sensitivity metrics than TAC-Q?
Yeah. So these are some of the other ones I experimented with, but I also experimented. Okay, this is there's like a lot of different metrics that I experimented with. So there's metrics that I was like, okay, well, right now I'm taking the loss, the language modeling loss, essentially uh, for a particular task. But what if I were to mask the loss in some way? Like for example, if I'm doing a multiple choice question answering, maybe I should only consider the single token that is like that is based on the answer, so the answering token, or perhaps I should mask. Perhaps instead of like because if you do the language modeling loss, the cross entropy is a one hot, like the ground truth is one hot, right? And it's
Mhm.
basically saying like, what is it like? If you were to change the model, I want to make sure that the model's output still aligns with that correct answer token. Um, but there could actually be multiple answer tokens that are equally valid, like or synonyms essentially. Um, and I should probably consider that as well. Right? Generally, I just don't want the output to deviate. And I tested a bunch of those things, and it turns out like performance is basically equivalent, or at least not different enough for me to actually include them. There's probably still avenue, like I probably still haven't explored the entire space, but that's kind of sad. Um, let's see. And there's some, and then also, okay, so here's a very sad kind of thing that happened. Um, in these previous papers where they had like outlier detection and stuff like this, you see these nice patterns. Like this is the importance for a particular weight matrix, and there's like actual rows and columns here of like
Mhm.
really important weights. And I observed the same thing in using the TAQ metric that we have now. It's the same row and column. And I was like, wow, no, it's like much easier to store outliers if they're in a single row. Because instead of using 32 bits per weight, per outlier weight, I can just use 16. And then like use it like and then just like specify the row index. So like I've half the cost of like preserving weights, of needing to save weights. And I was like I thought it was like really promising. Um, and then I kept trying to like make it work, except it just like didn't work. Like it like in at some level, if you use just the gradient, like it worked somewhat, but the reason it didn't work is because I had to consider uh the the relative changing weights. So like that QW minus W thing, that is
Mhm.
basically does not have any nice row column patterns. And if you did row column, then like you're capturing a bunch of weights that are not very important.
Interesting. So, do you know where this kind of row column pattern might come from that you're showing on the screen at the moment?
Yeah. So this is a consequence of how the gradient is computed for a weight matrix. Uh, the gradient is only computed. Um, let's simplify this to like a batch size of one example, right? So it's computed
Hmm.
based on a input row, input vector, as well as an output vector. So the input, let's imagine the input vector is like over here, horizontal, and the output vector is vertical. The
Hmm.
gradient of a weight is the input vector's outer product with the output vector, um, where the output vector is the gradient with respect to the output activations, and then the input vector is the activations coming into that layer.
Fair enough.
Right? And it turns out there's a bunch of huge outliers for the activations.
Oh,
Um, yeah, and that's why you see these thick columns.
this happens even when you go to large batch sizes, huh?
Still happens when you go to large batch sizes. Uh,
Oh, wait, that
like
doesn't really matter. I see it. It's always for a specific example here.
yeah,
And that's
exactly.
when you
And
see this. I see. I see. Mm.
this outlier issue has actually been troubling a lot of people. Like I'm doing weight only quantization, which is like still rather nice because most weight values are like similar to each other. Like there's not huge outliers. There are some outliers, but not huge outliers. But things like the gradient, right? And especially things like the activations of the model will have these giant outliers that are like 10, 100, or 1,000 times larger than the other values next to it. Um, and that means if you want to try to quantize the activations, uh, these values will be like completely clipped or like completely ruined. And it happens that these outlier activations are actually important for the model's functioning.
I wonder if these sort of normalized weight matrices, like NVIDIA uses in EDM2, would prevent that kind of massive dynamic range on the gradients.
Mm. So yeah, normalization. This is actually this is very interesting. Like, I mean, well, like every like layer in the language model will always have normalization layers. There's always a layer normal, right? RMS norm at least, right? That
Mhm.
apparently has
Yeah,
not
good
prevented
point.
this from happening. But on your point though, like this, people do try to normalize it, but they do it manually essentially. Like they realize, oh, there's a big outlier, like here, right? And then they multiply that with a small scalar value, so it like destroys the outlier. and then they do a equivalent multiplication on the weights to scale the weights up a bit, and then that ends
Um,
up basically preserving the actual output. Um, because the weights are like small, the weights are still like you can still quantize the weights correctly. Just don't have to deal with activations anymore.
I see. Well, I've got to go. Great talk.
All right,
Thanks.
thanks.
Awesome. Yeah, that was a great discussion. I really learned a lot from this. Really appreciate you making the time to present. This is the first time we've had someone present their actual original work, so this was a special treat for everybody. So we all really appreciate it.
Cool. Thank you for hosting.
Yeah, awesome. Cool.
All right,
Well, yeah, I guess we're about at time. So, yeah, thanks everybody for joining. Thanks to our presenter again. And yeah, we will meet again in a couple weeks. All right, have a
sounds
good
good.
day. Bye.
You too. Have a good day.